If your cell was a race car, then diabetes is driving it at its maximum speed 24/7 while feeding it dirty fuel.
Calm down, calm down, calm down, calm down, calm down!
This constant stress creates massive engine damage, and we call that oxidative stress. Luckily, your car has an internal mechanic. This mechanic's job is to clear out the gunk and replace worn out parts to keep the engine pristine. In your cells, this mechanic is called autophagy. But in diabetes, the damage is so relentless that the mechanic gets overwhelmed, breaks down, and the entire system fails.
I'm tired. I'm tired. I'm done.
This breakdown isn't just a broken engine. It's kidney failure, it's blindness, it's heart attacks, and that's all because this one single process is broken. This process, autophagy, from the Greek for self-eating, is your cell's essential garbage disposal and recycling unit. The terrifying part is that in diabetes, it becomes a double-edged sword. If it fails, your cells drown in toxic waste, and if it becomes too active, your cells can literally eat themselves to death, committing cellular suicide. We need to find the zone, not too little, not too much, because hitting that spot might be the only way to save organs from diabetes. So, how does this mechanic actually work? The key process is macroautophagy. A double membrane vesicle, the autophagosome, forms around the damaged material. It then fuses with the lysosome, where powerful hydrolases degrade the contents. But here's the most critical concept, the one that explains the overwhelmed mechanic: flux. Flux is the entire process, from formation to degradation. In diabetes, we often see a traffic jam. The mechanic tries to bag up the trash the autophagosomes form, but the garbage truck, the lysosomes, never show up. This toxic buildup of vesicles is a real disaster. Autophagy fails in diabetes because the central command center, the nutrient sensing signaling hubs, is overwhelmed. Back to our car, the brake in the car is called mTOR. mTOR is the mechanistic target of rapamycin. It senses growth signals like high insulin and suppresses autophagy. In diabetes, chronic high insulin keeps this brake permanently floored, preventing cleanup. Okay, now we know the brake. What about the accelerators in the car? AMPK and SIRT1. Opposite to mTOR is AMP activated protein kinase, AMPK. When energy is low, AMPK switches on autophagy, and in diabetes, it's often suppressed. This creates a cycle. Chronic high sugar generates high amounts of reactive oxygen species, ROS. That is the engine damage. This damage requires removal, but it also impairs autophagy itself. This is the loop that makes it worse. Now, this whole thing manifests differently in every organ. In the kidney, there are delicate filtration cells called podocytes, and these podocytes are dependent on autophagy. When autophagy fails, when flux fails, damaged mitochondria accumulate, causing podocyte death and kidney failure. And in the heart, perhaps it's the most controversial. The therapeutic window is so thin. Too little autophagy causes damage accumulation. Too much causes cellular self-destruction. And then in the eye it's so paradoxical. Activating autophagy is good for one type of cells, but not good for the other. Activating autophagy is good for the retinal neurons, yet in the retinal blood vessels, high glucose enhances autophagy, and this promotes pathological blood vessel growth that causes blindness. So, a single systemic drug could save one part of the eye while destroying the other, which means we need to be very precise. Researchers are developing drugs focused on restoring or fine-tuning flux. Some are even so well known. The hero of type 2 diabetes, metformin, works partly by activating AMBK, yes, the accelerator, thereby inducing protective autophagy. It was also found that newer anti-diabetic drugs like SGLT2 inhibitors and GLP-1 receptor agonists are demonstrating organ protection, and emerging evidence suggests they work in part by activating the AMBK SIRT1 axis. Good to know. Now, since the accumulation of damaged mitochondria, the engine junk, is the problem, the selective form of autophagy called mitophagy, means mitochondrial cleanup, becomes a prime target for future highly specific drugs. This is the smarter mechanic, the one that only fixes the broken parts. The ultimate challenge is moving beyond broad systemic activators. We don't need an on-off switch, we need dimmer switches, drugs that can be finely tuned and delivered specifically to the right cells. One last disappointing problem is that we lack ways to monitor this process in real time in patients. We don't have non-invasive biomarkers. The only way to monitor the process now is to take biopsies and...
I think I might just put a knife in
I
it.
think that's a really good idea.
See if it works. Oh yes, it goes in beautifully.
That means we can do clinical trials on actual patients. We can only try this on animals and tissues. Sadly, it's a long way to go from here. Targeting autophagy isn't about building a bigger fire or dumping more trash. It's about precision. If we can learn to control this fundamental process of cellular self-eating, we can break the cycle of diabetes and potentially prevent the complications that destroy lives.